So now we're going to pick up, and within the common emitter configuration of hooking up the BJT, we're going to look at the currents inside and how those result in external gains. So again, in the common emitter configuration, we're going to concentrate on this forward active mode. And again, that's just very similar band diagram to the MOSFET, except that it goes through two different junctions, two different PN junctions, instead of just regions within the same material as we saw in the MOSFET. So again, this is our N++, our P, and our N doping here. So in forward active, again, so this one is forward biased, so you're injecting these little orange electrons. So this is a forward bias junction, and the depletion width shown between the dotted lines. And then what we want is for all of them to be swept through and out of the device. So this one is in reverse bias to help with that collection. So we can envision the travel of a single electron here, but really to understand what's going on, we need to look at the minority carrier distributions. So if we carry down our depletion widths here, we can draw in our minority carrier distributions in the three regions. So this is distance along this axis, and we're going to eventually define some axes, relative axes in each of the three regions. So I'll just do that here. So this is x, and it goes from 0 to xb, which is the thickness of the base within the quasi-neutral region of the base. So from here to here. We're going to have another axis here, which is x double prime, which goes into the collector. And then for convenience, we'll use another axis here, x prime, which goes into the emitter. And of course, that's facing in the opposite direction. But in all cases, they're pointing away from the PN junctions, just like we've used to analyze PN junctions themselves. So the minority carrier distribution in this forward active configuration, in the base, we have a approximately linear distribution, and the minority carriers here are going to be electrons. So we have n of x here and n in the p-doped side on x. In the emitter, we have holes, so this is Pn of x prime. And then in the collector, because it's reverse biased, it comes up like this, and we have Pn of x double prime here. So the asymptotic values and the background, the values in the absence of voltages, I'm going to insert next. So this would be np naught, this would be Pn naught, and this would be Pn naught. Of course, each of these referring to the different doping regions. So remember that the N-type doping here is something like 10 to the 19. The P-type doping about 10 to the 17 here, and the n-type doping here, something around 10 to the 15. So all three of these numbers are different. I've just shown them schematically. So let's look at the collector current. So if we assume that all of the electrons that are injected from the base to the collector are collected, we're going to get a current, traditional current going this way. Notice that it's going in the opposite direction because of the negative sign of the electron. And sorry, I should use I, little I here. So we can, if we can assume that there's no recombination in this region, then we can evaluate the diffusion current here on the base side of this junction to calculate the injected current, and then assume that all the current makes it to the other side. So we have to figure out what that's going to be. So our study of the p-n junction has shown us that the major currents consist of the diffusion currents, and so we end up having to evaluate currents that look something like this. Diffusion constant times an area times a derivative of the carrier density with respect to x. So there's our diffusion current, and we're talking about right here at the edge of this depletion width. And if we make the assumption that this is a linear gradient, then this becomes a constant, and it's just going to be this concentration minus 0 here, and the 0 is justified because we assume that all the carriers that reach that point are swept through the depletion, through the reverse biased base collector junction at the edge of the depletion width there. So we have the gradient being NP of x equals 0 minus, 0 minus that over xb as our gradient, and then we multiply all the other terms, E dn times the cross-sectional area. And then we can look at this term here, and again, because this is minority carriers, we can actually know that the concentration there is going to be proportional to exponential to the VCB collector base over V thermal. So this is the voltage-dependent injection of electrons through this junction, which determines the concentration right there, and then this one is 0. And so in the end, we get some constant times exponential to the VCB over V thermal. So we're just highlighting the voltage dependence here. And interestingly, what it shows is that the current in the collector is dependent on the current flowing through this junction also. And that's where we're going to get our gain factors. So let's erase this part, and then we'll look at some definitions of the gain factors alpha and beta next. Okay, so over on this side, I've redrawn the sort of block diagram structure And we're going to look at the flow of electrons from here to here, which of course produces currents going the opposite direction. So the collector current here, what we wanted to do is go all the way through the device unimpeded, and that's the same as the electrons making it all the way through. Now we have also some injection of holes from the base to the emitter. So while we're raising up that electron emitter so that the barrier here gets smaller and putting it further into forward bias, what it means is we're also injecting holes back this way as we're injecting the electrons that way. So we want to minimize this hole injection current. And then also, there's some recombination that happens inside the base, especially if the base is longer than the diffusion length of the electrons in the base. And for that reason, we have to feed some more holes into this base to supply that recombination current. So what we'd like is for both of these currents to be as small as possible, and for these two things to be essentially equal. And we can define a ratio which tells us how well the transistor is doing by defining this alpha, which is the common base gain. So this is a gain factor which should be actually very close to 1, because as we said, we want the emitter current to be as big as we can make it, while the base current is as small, so that this ends up being close to 1. And we can kind of write this as 1 minus a very small factor epsilon. Now, we can, in the common emitter configuration, we can define a different gain, IC over IB, and this is beta. And this is sort of more directly visualized from what I was talking about here, that we want the, again, the base currents to be as small as possible and the collector current to be as large as possible. And so this number should be, something greater than 100 or something of that order. So we can also we can plot the collector current versus the bias on this second p-n junction here, and there is not all that much dependence because it's primarily determined by the forward bias on the emitter base junction. So for these different emitter currents, we can, so IE1 to IE4, we can define 4 different levels here, and each of these would be, the IC would be alpha times IE1 here. So for each of these values of the emitter current, and notice these indices are referring to this total current, not these subcurrents. So the collector current is just multiplied by this alpha. So what do we want for a good transistor? Let's summarize again. We want to minimize this epsilon so that alpha is as close to 1 as we can get, and we want to maximize this beta so that it's as large as possible. It turns out that there's relationships between the alpha and beta gain factors. So we can write beta like this, and conversely alpha is going to be, in terms of beta, written like this. Okay. All right, so now let's come back to the modes of operation for the device for a minute. We can look at the collector current versus voltage on across the entire device. So the voltage from here to here in our common emitter connected NPN transistor, and we can determine that the IV curves look like so. This familiar linear increase followed by roll-off types of curves that we see for the any kind of transistor. So what we can do is go around the Kirchhoff's voltage loop, and here's our emitter base collector, and I'll just remind us what this looks like here. So this is the VCC. Oops. And this is the VBB, and then we have RC, RB here. So if we define this as our voltage all the way across the device from the collector to the emitter, we can see that it's going to be equal to VCC and then minus the IC current running through this resistor here. And so that gives us this load line on the IV diagram. So I've put that in with its equation here. So all the way from the saturation point, where the curve begins to roll over, to this point where VCE is equal to VCC, we can have this forward active mode in operation. So any operating point can be found on these lines here. So let's look at what this means in terms of the reverse or forward bias of these junctions again, and how that relates up here. So the forward active mode, and I'm going to write down in columns here, we have the emitter base junction in forward, the base collector junction in reverse. At cutoff, which is actually going to occur right at this point, the injecting junction is still in forward, but the collecting one is actually just at 0. So this means we've brought this band up to its built-in potential only, with no external biasing applied there. So this next section in saturation up here, we're going to be in forward here, but also in forward on this one. So that would be actually bringing this band bending less than its built-in voltage. And then the last configuration, which we can't really reach in this circuit configuration, we would have to actually flip the transistor physically over. So that would be our inverse active, and in that case, keeping the same definition of this being the heavily doped N++ side. Oops. Then we would have this junction in reverse and this junction here in forward. And again, we would have to flip the, physically flip the transistor. So that relates the concepts of regimes of behavior and the IV curve for the device here, and written on the x-axis in terms of the total voltage across the transistor, which is going to be internally the sum of the voltages across the emitter base junction and the base collector junction here. So next, let's take a look at the actual minority carrier distributions and how those relate to the currents. And once we do that, we can actually go back and derive formulas or approximate formulas for the gain factors. Okay, so we've looked now a little bit at the currents and the definitions of the gains in the transistor. And now let's look at the actual derivation of those currents and how those relate to the carrier densities inside the transistor, and thus we can actually derive formulas for the gains as a function of the doping and other parameters of the materials and, of course, of the voltages. So I've reproduced here the diagram of the minority carrier distributions in the emitter, base, and collector regions. And remember our definitions for the coordinates. So we have the x-coordinate running through the base, and then the x-prime coordinate running through the emitter. And again, the positive direction is away from the emitter base PN junction. And then the x-double prime coordinate moving away from the the base collector PN junction into the collector region. So because each of these are PN junctions and we're looking at ideal behavior and injection currents, in each of these regions we have to satisfy ultimately the ambipolar diffusion coefficient, the ambipolar transport equation, but under the low injection approximation and the doped semiconductor approximations, we can reduce it down to the simplified form. So the diffusion constant d dx squared of delta, I'm just going to write it as delta n of x, and then minus delta n of x over tau equals 0. So this is the diffusion recombination form of the equation, and we're really only considering now the quasi-neutral regions here, here, and here, so that we don't have to worry about the E fields because they're 0 in these quasi-neutral regions. So we're not considering what's going on inside the depletion widths right now. And of course, this really is referring mostly to the base region here because I've written the delta n. But you could write the same equation just flipping delta n for delta p in these two regions, as we'll do shortly. Okay, so let's consider the base first. So in the base region, we can write first this delta n of x function, and this is going to be our delta n, remember, which is the actual concentration minus the concentration at equilibrium, thermal equilibrium. So this is going to be N B naught times x to the V B E over V thermal minus 1. So this is the ideal diode equation for this p-n junction. Now we're going to have to hit this with a cinch function. Because we're dealing with a small region in comparison to the minority carrier diffusion length in the p-type material here, we end up having to have a cinch function here of xb, which is the total width of the base, over L. And we're going to use the subscript B here to say that it's the diffusion length in the base. So it's the minority electron diffusion length in the base. Then all this term minus another cinch. And this is the same form of equation that we ended up with for, remember, for short p-n junction diodes. And then all of this over a third cinch. Okay, so this is our delta N B, of voltage. Now, these cinch functions look a little scary, but let's remember that the cinch is e to the x minus e to the minus x over 2. And so if we can approximate both of these functions and linearize them, we can greatly simplify this whole expression. So I'll draw here the actual cinch function as a function of some coordinate y. So the actual cinch takes off a little more than linearly, but for some region we can linearize it to good accuracy. So what we're going to do is kind of assume that this argument here is small, and that means that essentially we have very long minority carrier lifetime, or that we have very short base width. So both of those conditions can justify this. So after we make this linearization approximation, we can finally simplify this to be more compact here. So we still retain we're still retaining the ideal diode law, not making the small voltage approximation here yet. And then this is times xb minus x, and then minus x here. And my closing bracket, I'm sorry, is merging here with this diagram a little bit. So this is the linearized form. So without going through all the rigmarole of actually differentiating this, we'll eventually come back and talk about what these currents are in the different regions. But this is the simplified linearized form for the carrier density itself. So now let's look in the base and the collector, and I'll just point out the sort of key assumptions along the way. Okay, so let's take the emitter first. And in the emitter, we're going to sort of leave it ambiguous. We're going to write the general form. The first equation will end up looking a lot like this one, because you'll have the cinch functions, which are a sign that you're treating it as possibly narrow, small argument for xb over L. Excuse me, for the distance, the thickness of the emitter over the diffusion length in the emitter. So we would have xe, I misspoke. When you simplify it down, we can get a very similar expression here that you're going to have PE naught over the thickness of the emitter, and then the base emitter voltage over the thermal voltage, minus 1. And then times xe minus x prime here. So this is both the voltage and distance dependent whole concentration in the emitter, and then the collector comes last. Now in the collector, we're going to make the assumption that the collector is very thick or very long, so that we can not deal with all these hyperbolic functions, and we're just going to have delta P in the collector as a function of voltage, and distance is negative P collector naught, so that level. And then exponential dependence, so just this rising negative x over L, like that. So with these three equations, we can go through and solve for all the currents as a function of dopings and thicknesses and carrier lifetimes. So let's look now at how the different currents add up physically in the device. And now we're going to throw in some extra currents also having to do with non-ideal effects like recombination especially. And then we'll finally come back and relate those to the gain parameters alpha and beta. So here I've drawn a schematic that labels all of the current components that we need to worry about in our full treatment. So first, let's look at the totals. So over here we have our total current going into the collector, and again that means electrons coming out in an NPN device. We have the total current going into the base, and then the total current coming out of the emitter. And again, the particle fluxes are opposite if they're carried by electrons. The three orange components here, there's generation inside this reverse biased depletion width. There's recombination inside this forward biased depletion width. And then also there's recombination here inside the base that we need to worry about. And that one is JRB. So those are three generation recombination currents. Then we have sort of diffusion currents in in all of the quasi-neutral regions. So if we assume that right here at the edge of the depletion width, we can know the minority N concentration right here. So this is again our P plus and plus plus N regions. So right here at the edge of this depletion width, we have the current, which is due to electrons injected into the depletion width, evaluated right here at XB. So that's the one of the currents that we evaluated. Excuse me, it's the diffusion current due to the minority carrier distribution that we just derived inside the base. Then we have the back injection current. This injection of, if we're injecting electrons this way, it means we're injecting holes this way. So those are considered to come through the base. And then on this side, likewise, at this point right here, we can evaluate the current, which is electrons injected into this forward biased junction, and because of that, they produce a current going this way, and we're going to evaluate it right here at this edge. And then lastly, we have the current due to back injection of holes into this forward biased junction here. So when I'm saying, back injection of holes, it's this kind of current here carried by holes going this way, and over here on this side, this is reverse biased here. So we're really looking at some diffusion of electrons going this way for that current. Again, this one would probably be a lot bigger. Okay, so finally, again, we're not going to go through and derive each of these currents. We can just say that they would be found by taking the derivatives. So remember that J diffusion is E d by dx of delta n or delta p as a function of x. So in each of these regions, these types of currents could be determined from equations like this. And then the generation recombination currents can be determined from by using the non-ideal diode equation, meaning that we put the ideality factor in the denominator. So let's just skip to the summary of what determines alpha. So it's defined as the collector current over the emitter current, and there's a whole bunch of things we need to sum up here. So we've got our injected current over JNE plus JPE. This total injected current ratio. So this is really the ratio of injected electrons to injected holes. And we can give that its own symbol, gamma here, and that's the injection efficiency. Now the next term we have to multiply by is JNC over JNE. Okay, and if we look here, this is this current that starts there and ends up there. So really, if we flip it around in terms of particle fluxes, we're asking the question, what's the probability of an electron launched from this point getting all the way to this point here? So this has to do with recombination, and how well you can protect the the minority carriers as they travel through the base. And the last one I'm running out of space, but I think we can fit it in here. So this last one here is our delta, and this is the recombination efficiency. So we can group all of these different currents into three different components, multiply them together, and again what we want is that alpha be close to 1, meaning that each one of these efficiencies is large. So we want to minimize the recombination current here in the forward bias junction here. We want to make sure that the carriers, that the electrons, in the case of an NPN, that are injected make it all the way through the device. And we want to make this ratio as large as we can, especially by, in the case of a single material like silicon, our best chance to do that is to maximize the doping contrast between the N and P regions to make this injection efficiency high. Okay, so the last exercise we can do is to summarize these three factors from all of the expressions for the delta N's and delta P's that we got. And I'm not going to derive it, it's derived out in the book. But what we can see is each of these efficiencies can be reduced to a simple expression that involves only the parameters like doping and diffusion lengths. So this is the base and emitter doping ratio that I just spoke about, and then you have the diffusion constants for minority carriers in both regions, and then thicknesses. So those are the parameters that matter for the injection efficiency. And let me mention one other thing that can be done here. So what we've said is that, or what we've assumed along the way here, is that we're talking about a single material here like silicon. But what you could actually do is greatly increase the band gap of the emitter here. And in a much earlier section, when we were examining PN junctions, we saw that the injection efficiency is greatly enhanced. So basically, if you have a band offset that presents a very large delta EV compared to a delta EC in a heterojunction, you can completely suppress the back injection of holes here and promote the injection of electrons. And of course, you would have to take into account that these are doped in the opposite sense. So this band diagram would be, would have some bending, but I'm highlighting here the very large valence band barrier. So the variation here that I'm talking about would be called a heterojunction bipolar transistor, which is really important for realizing large amplification. usually implemented in 3,5 materials, although something like silicon and silicon germanium could also be used, where silicon would play the part of the largest gap material. So back to the last expressions here, we can get the transport factor. It ends up being a hyperbolic cosine expression, which we can approximate, again in the small argument approximation, to be 1 minus 1/2 of the base width over the diffusion length in the base, quantity squared. So again, we have to, we want to make this as large as possible, so we want to minimize this term that's subtracted here, meaning we want to make x be small and the diffusion length in the base very large. And the last term here ends up being 1 over 1 plus JRO over J S naught exponential to the minus V base emitter over V thermal. And I've made a definition here that the JR over here is going to be equal to J R naught exponential to the VBE over 2 V thermal. So because this is a recombination current, again, we end up with this factor of 2 in the non-ideal diode equation, because it's a recombination assumed to be in a mid-gap state. Okay, so we've managed to relate all of the parameters that go into the gain factor alpha back to the dopings and thicknesses of the individual regions. Now, once we have alpha, remember that we can relate alpha back to beta with some simple formulas. And thus, without having to actually solve the complete system, solve the complete transistor to get the beta directly, we can also calculate beta knowing these factors here. So what we've done, although I haven't worked out all the steps, is examined how the physical parameters, the doping, the thicknesses, and also the cross-sectional areas of the different junctions relate back into the performance metrics, which is essentially the gain parameters of this bipolar junction transistor. Now, when we were talking about MOSFETs, we mostly concentrated on sort of on-off behavior, although we did talk some about the nonlinearities. The bipolar junction transistor turns out to be a little easier place to talk about the concept of transistor gain. Now, I want you to think in your heads and go back and sort of apply these ideas of gain. You get a larger current or voltage in one part of the transistor when you input a signal from another. And these concepts apply to all transistors, not just BJTs. We're just using this as a convenient place to teach about the concepts of gain, because the equations are rather familiar to us, because it's composed of just back-to-back PN junctions instead of more complicated structures, as in the case of the MOSFET transistors. So again, this wraps up our treatment of the basics of BJTs, and in the next video we'll talk about some non-idealities.